He's my favorite character, Mr. Freeman. I think everybody knows him. So, so we measure the market, as you know, or maybe don't know, but you do now. We test things also, make sure that the vendors are telling the truth, and we write reports about it. The organizer of this, who is a fellow by the name of Bobby O, who was standing here a little while earlier, asked me if I would come and give a brief presentation, which was based on this book that I most recently wrote. And I did this in a semi-private session at GDC, so if any of you attended that, this is going to be a little repetitious. But it's an interesting story, and I'd like to tell it. And it's the story of how did we get here? How did computer graphics get to where it is today? Basically, TV was the prime movement, if you will, for getting the cost down on CRTs. And CRTs is the biggest element at the time, and its subsequent LCD panels. But this is where we could actually see images. And until TV came around and mass production started, these were just laboratory experiments. So we got TV, we got pictures coming through the air, magic, and then we had a little problem, and that problem was called World War II. And right after World War II, where the United States was the sole possessor of atomic weaponry, the Russians, through various means, it's another story we could talk about, obtained the ability to build their own nuclear weapon. And when they did that, it frightened the hell out of most of the world, especially the United States, because at the same time, Russia developed a long-range bomber, which was pretty much a copy of the US's long-range bomber, the B-29. But nonetheless, this thing had large enough fuel tanks and big enough engines that it could fly from Russia over the top of the world and down into North America. And that made a lot of people nervous. So to counteract that, the United States and Canada installed the SAGE system, and I can't remember what that acronym stands for, something about ground something. But what was interesting about SAGE is, and I don't know if this picture shows you or not, but now we're doing graphics. This is not a scanline representation like we had on TV. So he's doing real graphics, and what he's holding is a light pen, and the light pen can pick up the light from the screen and know where it is in time for the coordinates, and he can use that as an identification. And that's what they did, is they pointed to radar images of aircraft and said, who is this? Do we know who this is? And if not, we got to do something about it. Now, the interesting thing about this, aside from the large graphic screen, is this guy is sitting in Massachusetts, and the data he was getting was coming from a ring of radar stations right at the Arctic Circle, which was called the DEW line, and the data from them was sent down to Massachusetts on phone lines. So this was the beginning of the internet also. So we started computer graphics, we started the internet, we started interactivity, all of this because we were afraid that the Russians would come and bomb North America, and they had the means to do that. So that's where it got started. And when I tell this story, people go, nah, really? And that is in the late 50s is when that got started. This is John's reading test. Anybody can read this gets a special star on their badge. But, and hopefully Intel will let you have a copy of these slides. But basically what it's trying to show you is that there's shading, math, art, computer technology, display, et cetera, et cetera. A lot of parts go into making computer graphics. And they went in at a asynchronous rate and from all types of different sources. Part of this book that I keep referring to talks about how we got the math to do computer graphics. The thing about computer graphics is it's mostly math. And if you don't like math, then your other choice is to build hardware or to be an artist if you want to be a game developer. Don't laugh. What kind of games will we have if we didn't have an artist? So, and here's another eye test, thank you. No extra charge for the eye test. But basically, this is trying to show the route and the development over time of the various major developments in algorithms. Now, there's a parallel chart that goes like this, and this is showing the hardware path. And then Where's Kathleen's quote? That's my favorite quote. And it's true, because one of the first things that was done with computer graphics in the early 60s was to build a game. And we kept on building games. Now, it turns out, nobody really thought this ahead of time, but it turns out games are an excellent way to build simulations and also to test the performance of a computer. Turns out that when you run a game against a computer, the game taxes everything in that machine. And this was just a lucky happenstance. It came about because in order to get realism, we had to ask for more and more and more from the computer. And as a result of that, I came up with this little phrase I like to use, that in computer graphics, too much is not enough. And I offer that statement because everyone says to me from one time to another, well, when are we going to have enough computer power? Don't we have enough computer power now? And the answer is no. And the reason I can say no so emphatically is until we get to the point, whether it's VR or on a screen or where, that we absolutely, totally suspend disbelief and forget that we're looking at or involved with a computer, till we get to that exact moment, then we don't have enough computer power. And that exact moment, by my reckoning, is so far out in the future, I hope I live to see it. But look at where we've gone. This is 1996, and at the risk of being a sexist pig, I'm going to tell you that the big controversy and discussion at this time was, how many triangles, how many polygons can we get? And I remember talking with some of the people who developed this, and their quest was to give Laura better boobs. They wanted more polygons for that. So look where we are now. This is 2 years old. Every strand of hair is rendered and is physically movable. Look at her skin tone. Her eyes move, her eyes blink. She smiles, she cries. She makes noises while she's running. This is such an extraordinary simulation. This is a 2-year-old game. And the other thing you have to keep in mind is this is going to run and is running at HD or better at 30 frames a second or better. This is a real-time simulation, physically correct, of a human interaction. And it's still not good enough. So you guys are developers. What's your opportunity? What's your TAM and so forth? First of all, look at your choices. Well, here's your choices down here, and here's your obstacles in between. And the reason there are obstacles is because there's no straight line. There's no clear path. You have to know all the APIs, you have to know all the OSs, you have to know the I can't say the word, but the differences between the platforms. Because if you build a game, you want it to run on all those platforms if you want to get to the 270 million people that he was just talking about. So there's the universe as we see it. Now, this is a slightly controversial chart because, as he said, that everybody's got their own view of what this market is. And what it really comes down to is how do you measure it? What's your methodology for measuring it? And the methodology can vary from day to day, can vary from hour to hour. And one of the points to make here is that when you talk about PC gaming, it's difficult to be specific about it. I can be very specific about consoles because when we measure the console market, we know that the consoles are used for gaming 100% of the time. It's a single function device. Even though you can play movies and do other things on a console, people don't buy them for that reason. They buy them only for playing games. A PC is different. A PC can be used for multitudes of things and play games. And so what we've tried to do in another report that we have is to measure the purchasing influence of games on PCs. Now this chart doesn't represent that. That's a report that we offer that talks about the market size in dollars. What this chart represents are units. And the units in this case are based on discrete graphics boards in the category of enthusiast and mainstream, and discrete GPUs that are in similar laptops. So this is a hardware per unit measurement. You're going to hear other measurements today expressed in dollars, and it's not going to line up properly, so I don't want you to be confused about it. That's the reason I'm mentioning it. The next phase of computer gaming is in immersive reality. And the holy grail in immersive reality is the holodeck. I'll just give you a little quick historical sketch on that. The holodeck was first mentioned by a science fiction writer by the name of Asimov, who had this thing called a magic room. And this magic room was where children could go and play, and they could play in a very simulated environment. And in this particular story, the environment was a jungle or a zoo, and the parents got annoyed with their kids spending so much time in there. Mind, this was written in the 60s, and the parents got annoyed with their kids playing so much time in there, so they went in there to correct the situation, and the lions ate the parents. That's how real it was. God, his name just jumped out of my head. The guy started Star Trek. Roddenberry, thank you. He also came up with the idea in a animation that he did first, which was called Star Trek, and then brought the idea into the Star Trek series. Now, a lot of people think that caves, which are 3 to 6-sided rooms that you can walk into and get immersed in, stereo vision glasses and haptic feedback and so forth. People thought that caves were the genesis for holodeck. It was just the other way around. The holodeck caught the imagination of some people at University of Illinois, and they said, hey, we could do that, and they built these 6-sided back projector systems for it. So that was the beginning of immersive reality. And then I'm taking big jumps here because I have a limited amount of time, but we moved forward and kind of plateaued. And you've all seen the picture of Donald Sutherland, Ivan Sutherland, with the glasses hanging from the ceiling, and he's looking out at it. And that was probably the first actual headset, and that was done back in the 60s also. And it kind of, didn't go anywhere for a long, long time. The primary market for virtual reality head-mounted displays has been a little bit of scientific for surgery training, some industrial applications. One that I like to talk about is welding, and the military being the big funder of it. And these HMDs for those applications typically start at $10,000. So when Lucky started pushing his notion of a head-mounted display and trying to drive down the cost because of his fascination with it, we started to hear about consumer-based pricing. Now, when Oculus was bought by Facebook at the outrageous amount of $2 billion, that inflamed everybody's imagination. And anybody who had ever heard about VR or had any desire to be in VR took that as being the turning point, the catalyst that the market was now going to explode. And one measurement of that is that last year we had 1 consumer HMD and 6 industrials. And today we have over 40 and more coming. So this is an explosive situation. We've seen this before. It can't last. You can't have that many suppliers into a market that doesn't have any content to support it. It's just there's going to be a lot of heartbreaks out there and a lot of disappointed investors. And so I encourage you not to get too enthusiastic about this. So then I want to do a quick update on what's going on in the future, what we think is coming in the future. Surely you've heard about Vulkan. Vulkan is the I won't say replacement, but let's say the next evolution in the Cronus family of APIs. They're well known for OpenGL and OpenGL ES. Vulkan comes with a new construct, and the construct doesn't oblige you to use the library that is associated with, say, OpenGL. You can use the library that's with the game engine. And all the game engines now have very extensive libraries, so it's a no-brainer almost to do that. But Vulkan has one other thing with it, which I didn't put up there, I'm sorry, a thing called Spire, S-P-I-R. And what Spirit is going to do for you is it's going to allow you to easily, heterogeneously blend graphics and compute using OpenCL. And that's a really, really big breakthrough. The second breakthrough on Vulkan, and DirectX 12 is going to have the same characteristics, by the way, is that you'll be able to run asynchronously shaders, which means that you can do real parallel processing, and it means that you're almost approaching a MIMD situation when you can do that, because now you can have multiple kernels running simultaneously and completing at different times and then picking up the next one. And those kernels can be either graphics and or they can be physics and possibly even AI if the AI can be constructed properly. So this is big news. This is going to speed things up in terms of processing time significantly, and it's going to allow you to scale your games to the function or the level of the shaders in the GPU. So more shaders, game goes faster. Or conversely, more shaders, the game is more beautiful. That reminds me, I want to tell you a little bit. There's a fellow by the name of Jim Blinn, who's the father of a lot of graphics features that we take in effect. And there's a thing called Blinn's Law. And Blinn's Law says that the rendering time for, his model was a cinema, the rendering time for a movie doesn't change regardless of the increase in processing time. And you think about it and you say, well, that's counterintuitive. How could that be? If the processing time is reduced, then the movie time should be faster. It isn't. It's because in computer graphics, too much is not enough. The people who are making movies and the people who are making games want the most beautiful picture the most realistic image that they can possibly get. So you give them more processors, they're just going to use those processors. It's still going to take just as long to create the damn game or the movie, but it's going to be much, much more pretty. Boom. So global illumination and ray tracing, these are things that we keep talking about, we keep hoping about. There's been some really interesting work done in global illumination. ARM bought a company a little over a year ago that's got a terrific global illumination model in it. I encourage you to look at that if you're doing anything that is associated with ARM. And in ray tracing, there's been 3 or more breakthrough developments in the last couple of years that will be realizable by developers like yourselves probably as early as the end of this year. We're finally able to find tricks to allow us to use a GPU for ray tracing. GPU is not well constructed for ray tracing because of the unpredictable branching that goes on in a ray tracing model. But NVIDIA just put out a paper where they found a nifty way to do it kind of in post. There's some new algorithms that have a different approach to how they plot. And there's a couple of companies, 2 in fact, that are going to build hardware accelerators for dedicated ray tracing. So all that's coming, and my prediction is that by 2016 we will have, in the AAA games, we'll have ray tracing as a major component. Now that's not to say that the entire scene is going to be ray traced. It won't be. It'll be what's called zonal or hybrid ray tracing, where you'll ray trace the elements that need it. Things that need it are automobiles, for example. There's not a straight line on an automobile. It's just a whole big bunch of curves, and those curves all reflect light, and the better you can render that, the better looking it is. Just a sidebar to let you know about cars for a minute is that automobiles are no longer photographed. When you see an ad for an automobile on TV or in a magazine or someplace, that's a computer-constructed ray-traced image. And it's been like that now for about a year. It's almost 100% now. And so that's an example of how we're using computer graphics in a consumer situation. Now, mind you, that doesn't get generated at 30 frames a second. So that's the reason you have to use zonal or hybrid techniques. And then VR and AR are the leading edge things that we're talking about. Everybody is excited about VR. My view is that, and you heard it expressed by the previous speaker, that my view is that as wonderful as it's going to be, and it's pretty wonderful already, you're just not going to wear that headset all day. It will get heavy. It'll get tired. It's a little impractical. So we need another model We also need higher resolution. The screens just aren't high enough resolution yet because you put an HMD on, you see the pixels, and that's not the way life looks. So we're willing to put up with that. Our brain is amazing. Television would never have worked if it wasn't for our brain compensating for the poor quality of the image. And we'll do the same thing in VR for a long time, especially if the content is good enough. And the content is probably the weakest link in the chain. Well, it's the second weakest link. The feedback loop or latency is the weakest link, but the content is really, really critical. And this is where the game developers really have a strong role to play, because VR should not be treated as a image gimmick like 3D was in the olden times, where things jut out at you from the screen. At a recent conference I just attended in Germany called FMX, they had a dozen VR demonstrations there, and 50% of the demonstrators, who were people who should have known better, made the demonstration of things like roller coasters and bad airplane flying. And the point being is that they kept moving the horizon back and forth, so the net result was everybody walked out there and went, I gotta go, because they just felt lousy because the latency and the disorientation with the moving horizon is just too much for our little brains to handle. That's one thing we have difficulty with. But think about a racing game where you're just going back and forth, you're not tilting the horizon. That's a game that could be really exciting in VR. And so if you use a little common sense and don't try and be exploitive of the technology and make a story out of the VR aspect of it, then you have a better shot of getting happy customers. Now the risk here is that if you don't do that, and if other content developers don't do that, and the experience of VR is just one that is disgusting because we don't feel good after a while, guess what that's going to do to the market? That's going to put a bad taste in everybody's mouth. And I used to tell my kids when I was raising them, be careful of your reputation. Whether it's good or bad, it's damn hard to lose once you get. Well, that's what's going to happen to VR if we're not careful. If VR gets tagged as being the sickness game, guess what's going to happen to VR as a market? It's going to disappear. So my advice to you, and I realize I'm lecturing now, I apologize, but because I've seen this movie before, and they all have bad endings. I hope this one doesn't. Use some common sense in your game development. And I think that's it for me. All right, Joe, just to wrap up, you can read this. I don't need to read it to you. Yeah. And then just a shameful plug. Shameful plug's coming. Stay tuned.
You mentioned how Vulkan was going to change the way that communication is done between compute and graphics. How is that going to be different from the way we do interop currently with OpenGL?
This thing called Spear, S-P-I-R, and I encourage you to go to Cronus website and look it up. Spear allows you to write code in a different fashion so that you can write one line of code which will engage OpenCL calls as well as drawing calls. And so it's more efficient. It also has a certain risk with it. If you write bad code, things are going to go to hell real fast, and the debuggers are going to have a hard time tracking them. The compilers are just going to break completely. So the good news is you're going to have more flexibility. You're going to be able to write tighter relationships between graphics and compute, but at the same time you're going to have to be a serious law-abiding programmer and follow all the constructs. Does that come anywhere close to answering your question? Okay. Any others?
I got one. The question I have is, you made really good points about when VR doesn't work and how not to exploit it. What have you seen in your travels that is an example of a paradigm of how to do VR right? If you could name names or platforms, anything, to give us a clue as what you admire.
Okay, so I have a certain advantage in that I get invited to see things early. And the work that I've seen being done at AMD, doing a thing, AMD has a SDK they're calling Liquid VR, and NVIDIA has a similar approach, but I can't remember what they're calling it. But the point is that they've come up with this anticipation of frame rendering so that they can get a frame generated much sooner than you normally would through the typical graphics pipeline. And in VR, every millisecond counts. So by this next frame generation technique, and by the way, you have to use a lot of GPU horsepower for this. You know, two GPUs are the recommended, one for each eye. That's not a joke, and that's not a sales pitch for these guys either. That's just what it takes. But advanced rendering is the real trick, and the closer you can get to the feedback loop, we used to refer to this as the pilot's neck, you know, because the pilot would get out of sync with the simulator. That's the trick. So the good stuff I've seen has all been, unfortunately, experimental. I can't say you can go out and get this game and put on this headset and then run that machine. It's not quite there yet, but the foundations for it have been laid and are getting better. And so if you guys decide to design for VR, you have to learn about milliseconds. You have to learn about the feedback loop between the action-reaction. The worst thing that can happen, and you've seen this, you've done this with your mobile phones, for example. You push a button and nothing happens for whatever reason. So what do? Push the button again and again and again and again. And guess what you've just done? You've just queued up 20 commands. Well, that's the kind of thing that would kill a VR situation. If you press the mouse button with the anticipation of firing a weapon, let's say, or doing something, and nothing happens because of that millisecond loop, multi-millisecond loop, then you're going to push the button again. And if you keep doing that, you're just basically going to break the game. The game's going to crash because it can't deal with all that input. So I can't answer your question to the degree that you asked it, other than to tell you there is light at the end of the tunnel.
My question is for in terms of that input loop. I think the head mount, the head tracking is more important than like a button or action push. And I was curious what sort of frame rate. I've heard like 90 is a good one to sort of shoot for in terms of to get that feeling of immersion. Because if you don't have the good head tracking, you don't feel like you're there, and that's the first checkbox you need to get somebody feel like they're really having a VR experience.
90 is a good goal. I've heard 120, and the model there is think about 60 per eye, for example, is one way to think about it. But it's again back to computer graphics axiom: too much is not enough. To her point, until you can not notice that you're in a VR hardware experience, when you can lose the consciousness of the artifacts of the hardware and get engrossed with the story, with the content, the game, that's when we have good VR. And so to her point, if I turn my head, assuming the horizon's going to stay stable so I don't get sick, but I turn my head, I know I've turned my head. I want this machinery on me to also know I turned my head. And not only do I want it to know I turned my head, I want it to know precisely how many degrees, in fact, tenths of a degree, I've turned my head.
I was wondering if you know anything about WebGL and what you think of the state of WebGL is compared to today's graphics.
I know a fair amount about WebGL. I've been a proponent of it for quite some time. I'm going to answer your question, but I want to inject this before I forget. There is another element that you all should be aware of, which is called WebVR. There's a fellow by the name of Tony Parisi who is promoting that. And WebVR is similar to WebGL, and so now I'll get back to what WebGL is, and then somebody, if I forget, remind me to come back to WebVR. So WebGL is basically browser-based compute. And we have in the the scientific commercial side of the market, CAD companies, for example, are now doing web-based or browser-based applications, which means that the burden of software load on your machine and the necessity for super high-performance graphics is being reduced to the level of how well you can drive a browser. But the code execution is done elsewhere, and the browser is basically becoming a window. It's almost a throwback to something we had years ago called X Windows. So with that model, you can do things like remote graphics. And there's a company called Frame, which used to be called Mainframe 2, and they are offering a delivery system that's very fast through a browser using OpenGL for the delivery of, using WebGL for the delivery of games and or other types of content. So WebVR is the same model of using a browser for your web experience. And if you go to the WebVR webpage, and I think it might be webvr.org or something like that, you can find some really interesting code examples there. And if this is something that really interests you and you can't get a good link to it, send me an email, jon@jonpeddie.com, and I'll put you in touch with Tony, and he'll give you the real stuff. Yeah, another one.
Yeah, a quick follow-up question to that is, do you think WebGL is actually going to become like a first-class citizen with native graphics?
I'm laughing because I think that's a political question. And the reason it's a political question is because there is such legacy software and such an incredibly large installed base and such vested interest that there's going to be some very large companies, who I'm not going to name, but you'll figure them out soon enough, who are going to push back on WebGL because it doesn't suit their purposes. I think it's an elegant solution. I think it has its place. I don't think it's the total and only solution, but it certainly does give us another channel, another mechanism for delivering content. It won't become universal, I guess, is the answer to your question. Well, not for a long time anyway. We done? Time for lunch? Nope, one more.
Where do you see SVG evolving to support some of the advanced concepts?
I hadn't thought about that for a while. The question is about scalable vector graphics, and that derived from 2D and then evolved into 3D. It's primarily used in scientific applications. There's a few games that I can think of that have used it to some degree of success. I think it's going to be around, but it brings a computational load that some people don't like. It's difficult to get adequate rendering, so I think it's just going to kind of hang out there on the side. Is that okay with you?
The new standards for browser, HTML5, CSS3, they're pushing SVG as the core component for doing vector graphics.
And to that point, and back to the guy was talking about WebGL, so that's the same idea. And one of the reasons you have to do that is because you've got to get the load off of the client side of the process, and going to vector graphics is one way to do that. Is you can reduce yourself to just shipping coordinates and then just drawing simple lines.
I don't know if it's too futuristic, but when you were talking about Lara Croft, I was thinking about like the emotions, and my first, I thought about AI, like artificial intelligence. Have you seen anything where you can like see response and create emotions?
Yeah, there's two things I want to say about emotions. Your permission to keep talking. Number one, God, I can't remember the name of the company now. It's a Japanese company. They just ran some tests on emotive characters. And in this particular test, this is not in a game yet. These are, like I say, just test runs. But in this game, the character is confronted with an emotional rendering scene, and the character cries. Now that's interesting for a whole bunch of reasons. Think about what happens to your face when you cry. Think about how your face, crunches up in strange and unusual ways. It's not a normal appearance. Your eyes change, water emits from your eyes, maybe moisture comes from your nose as well. I mean, all kinds of things are going on now that weren't normally there, and the rendering of that, just the rendering of it, is extremely challenging, but the physics, all the little engine motors that we have in our face, now really become important, because now we have to put more of them in the face to do that kind of emotion. So it's probably the next major breakthrough in computer games and in special effects for movies is to get the emotive content of the character. The flip side of that is your emotions. And I hope today you're going to hear about a game that takes advantage of Intel's RealSense. The game is called Nevermind. It's put out by a company called Flying Mollusks. And without being too much of a spoiler, I'll just tell you that this game, using the Intel RealSense, measures your emotion. And if you get really caught up in this game to the point where your heart rate is going up and maybe you just need to take a break, the game fuzzes out. And I can't remember if a message comes up. At one of the demos I saw, a message comes up and it says, perhaps you should take a break. Calm down a little bit. So stay tuned for that. I hope someone from Intel or Flying Mollusks is here to talk about that, because it's a good game, by the way, also. It's a very intriguing game, and it's got this aspect of it. It's just the first one of many that's going to show up.